So here's a few examples that we'll continue from the last time, talking about the directional derivative and the gradient of a function. So this is just your basic type, find the gradient, just sort of a plug and chug type of thing. So if we want to find the gradient of this function, f of xy is e to the 2x plus 3y, all of those in the exponent there. So if I remember my definition of the gradient, we're going to need the partial with respect to x and the partial with respect to y in the I and j direction. So we'll go ahead and compute those. So the f sub x, this is going to be e to the 2x plus 3y times derivative of that exponent. So with respect to x, we just get that 2 that's out front multiplied there. Same thing for the y, f sub y. This is going to be derivative of e to the 2x plus 3y, which is the same thing, times derivative of the exponent, which in this case with respect to y is just the 3. Alright, so we get 2 times this e to the power and 3 times this e to the power right there. So there's our gradient, just this f sub x in the I direction, f sub y in the j direction. Normally with these, rather than writing the i's and j's all over the place, I'll put these in the component form with the angle brackets. So we have the angle bracket of 2 e to the 2x plus 3y, 3 e to the 2x plus 3y. And that's it. So if you can compute a partial derivative, you can compute the gradient. These are not too bad. Depends on what function you get, of course. So anything like this, now if I want to plug in a point, then I can tell the specific direction of the gradient at that point. But as far as a function goes, this is the gradient function right here. Alright, so here's our example 2. Compute the directional derivative of f of xy equals the sine of xy at root pi, root pi. So same value for the x and y coordinates. And we want the derivative in the direction of 3 pi I minus pi j. Alright, so in the direction of that guy right there. So the first step here is to remember my formula for directional derivative. So the directional derivative I can get off of this gradient dotted with this unit vector. So one, we're going to need these partials for the gradient, and the second thing, we're going to need to unitize this vector right here. So here's the partials. So I get partial with respect to x. So this is going to be the cosine of xy times derivative of the inside. So with respect to x, the derivative of the inside is just going to be y. So I get y cosine xy. Partial with respect to y, same thing, cosine of this times derivative of the inside, so that gives me the x times cosine xy. Alright, now I can plug in those points. So plug in the root pi, so we get root pi times cosine pi, that's negative root pi. Cosine of pi is negative 1. Same thing for the f sub y. So root pi times root pi is pi on the inside here, and then multiply that cosine of pi, which is negative 1, times a root pi on the outside. So there's my two values for the gradient. So gradient at that point, sometimes written gradient f naught to symbolize the p naught. At that point we have negative root pi, negative root pi. Alright. Next we also need this u. So to do the dot product we're going to need the u, and this has to be a unit vector. So the unit vector, right now we have 3 pi and pi. So we'll go ahead and divide by its length. So the square root of 3 pi squared plus pi squared, that gives me pi times root 10. So 9 plus 1 is 10. Bring out that pi squared from outside the root. Pi's will divide out in each component, and we just get 3 over root 10 and 1 over root 10. Alright, so there's my unit vector. Oops, wrong way. So now off of that, now I just have to compute the dot product. So the dot product there, gradient of f naught dot u. So this is going to be negative root pi, dotted with this other guy. So just first components multiply plus second components multiply. So we get negative 3 root pi over root 10 minus root pi over root 10. So that's negative 4 root pi over root 10. If you want, you could leave it like that. That'd be fine. If you want to combine this into some sort of single root, that's okay. But anything along this line is going to be fine. Alright, so there's our directional derivative. This tells us we have a negative slope, so we're going to be decreasing in the direction of this 3 pi I minus pi j. Alright, another example here. Find the direction from p naught 1, 2, in which the function f of xy equals 1 minus x squared minus y squared increases most rapidly, and compute the magnitude of this greatest rate of increase. Alright, so when I read through this, I notice increases most rapidly. So remember, the gradient will always tell you what direction you increase most rapidly in. So really for this function, we're just looking for the gradient of this thing at this point, and then the magnitude is just going to be the magnitude of the gradient. So we'll go ahead and go off of that. So first thing, find the gradient and its magnitude at that point, 1, 2. Alright, to get gradient, we just need some partials. So the partial of f with respect to x, so this is just going to be negative 2x from this x squared component right here. The f sub y, that's just going to be negative 2y from this negative y squared that's right there. And now we plug in our values. So at 1, 2, the x is 1, so we'll just get negative 2 for our function. At 1, 2, the y is 2, so negative 2 times 2 gives me negative 4. So there's the negative 2 and negative 4. That is my gradient, so that is the direction of the most rapid increase. They didn't ask for a unit vector or anything like that, so we can just leave it. You know, you could divide by 2 or negative 2 if you like. Or not negative, but you can divide by 2 to get the length out. But it's not really necessary for this, so I'm just going to leave the gradient as is. We do need the length though, so the length is going to be the square root of this negative 2 squared, which is 4, plus negative 4 squared, which is 16, so that gives me square root of 20. Alright, so once I've got that, then that's it. So direction which it increases most rapidly, negative 2I minus 4j. The magnitude of the increase, square root of 20. So this is just a basic question about, you know, what is the gradient, what is its size, just phrased a little bit differently. Alright, I think there's 2 more questions here, so I'll go on to this next one. Find a unit vector that is normal to the graph x squared plus y squared equals a squared at the point p naught, which is at x naught, y naught on the graph. Assume that a is a constant. So for this one, if we want to find a unit vector normal to the graph, so remember, if we're normal to the graph, that's going to be same thing as the gradient. So another way again to phrase this, a request for the gradient. Alright, so I'll go ahead and see what happens there. So the normal, okay, found using the gradient, and now we get f sub x and f sub y as my gradient components. So f sub x is just going to be 2x. The f sub y, just 2y, derivative of the 2y, or y squared gives me 2y. And so at the point x naught, y naught, I don't know what that is, but I can just plug in x naught and y naught. And so I get this partial with respect to x is 2x naught, partial with respect to y, 2y naught. Alright, there's the gradient. So the gradient at that point is 2 times x naught, y naught. Okay, so I just had those 2 components right there. And since they asked for a unit vector, we'll go ahead and unitize. So the magnitude of this gradient is going to be 2 times the square root of x naught squared plus y naught squared. Really, this is the same as a squared from this original formula. So x squared plus y squared is a squared, no matter what the x and y are. So anything on this graph is going to give us a squared for that guy right there. So I got 2 times square root of a squared, which is same as 2a. Alright, that means our vector is going to be this 2 x naught y naught divided by 2a, or just 1 over a times x naught y naught. The vector x naught in the I direction, y naught in the j direction. This is pretty straightforward except for that last step. Whether or not you saw to change that back to in terms of a, you may not have seen that, but that is one step I can do to change things. Notice this is just a vector that's going to point right back toward the origin, or away, directly opposite, away from the origin, on this circle of radius a. Alright, so here's our last problem. So we have a metal plate covering rectangular region from 0 to 6 in the x direction, 0 to y in the y direction, or 0 to 5 in the y direction. And it's charged electrically in such a way that the potential at each point is inversely proportional to the square of its distance from the origin. If the object is at the point 3, 4, in which direction should it move to increase the potential most rapidly? So this is sort of an electricity problem here, trying to increase the potential or voltage. Right, so in looking for a direction to increase most rapidly, all we're going to need is the gradient. So remember, anytime I'm looking to increase most rapidly, that's going to be the gradient. So we want the gradient of f at the point 3, 4. So to compute the gradient, first I need an equation. So for this guy, all I have is that we're inversely proportional to the square of my distance from the origin. So potential is inversely proportional. That means I can set up a proportion where potential is k over some value. And in this case, it's going to be k divided by distance from the origin, squared. So the square of the distance from the origin is just k over d squared. Now that d, I do want to put that in terms of x and y, so I'll work on that now, but this is what the inverse proportion means. I just have k divided by the square of the distance there. So if d is the square of the distance from the origin, let's go ahead and find that distance to the origin. So for any point x, y, distance to the origin is just square root of x squared plus y squared. That's my basic distance formula. And so when I plug in that square root to this square, now all of a sudden we're going to get p is equal to k over x squared plus y squared. So when I square the root, it goes away, and I just get k over x squared plus y squared. So there's the function that I want to go ahead and use when I'm trying to compute the gradient. Alright, so for this I'm going to rearrange this a little bit. Write that as k times x squared plus y squared to the negative 1 to compute these partials. So if I do that, derivative here is going to be just the constant k times derivative of, times this exponent, negative 1, so I get a negative and a k, of x squared plus y squared to the 1 less power, negative 2, times the derivative inside. So the derivative inside with respect to x is just this 2x, with respect to y is just the 2y. So we get the partial of p with respect to x, negative 2xk times x squared plus y squared to the negative 2, partial with respect to y, negative 2yk times x squared plus y squared to the negative 2. And now we just need to evaluate at 3, 4. So this is going to give me the components of my gradient. We want it at 3, 4. So if I plug in 3 and 4, then I'm going to get negative 6 times this x squared plus y squared. So that's going to be 9 and 16, which is 25. And then 25 to the negative 2 means dividing by 25 squared. 25 squared, that gives me the 625. So here I get negative 6 times k divided by 25 squared, which is 625. And that should be a negative out front. So let me go and put that in. So let's put in a negative there. Same thing down here. I'm going to need negative for that one. So this one we're going to get p sub y is negative 2yk times this x squared plus y squared to the negative 2. There's my partial. Plug in 3 and 4. So y is 4, so I get negative 8 out front times k times this 25. 9 plus 16 gives me 25 to the negative 2. That negative 2 means dividing by 25 squared. 625 again. So we got negative 6k over 625, negative 8k over 625. So there's my gradient, and if I want, I can factor out that value of k. I can't factor out the negative, that changes the direction, but any positive values you can factor out. Alright, so there's that guy, and then the last step, since any direction that's parallel to the gradient will work, we don't really need the k that's in front of that. So if we want to, now we can just write it this way. The direction of greatest increase will be negative 6 over 625, negative 8 over 625. So that k, since it's parallel to this vector, you can just say it's in the direction of this vector. You don't need the k to give you a different length outside. So that's the direction of greatest increase in our potential, and then we're done. Alright. If you have any questions, be sure to let me know. You can email me or post on my website, like I said in class. But make sure you do look at these. All of these are just basic gradient problems. Of course, your functions can be more difficult in some than in others, but be sure you know how to compute the gradient and use the gradient to give you a directional derivative.